This slideshow is about the style of volcanic eruptions. As you should remember, eruption mechanics, the way in which a magma erupts as a volcano, is controlled by two main variables, viscosity and volatiles, the two V's. Viscosity refers to how stiff or fluid a given magma is, while volatiles are the dissolved gases that are present in all magmas. In some cases there are a lot of volatiles, in others there aren't very many. And it's the relationship between those two things, viscosity and volatile content, that determines whether an eruption will be, for example, explosive, like the one here on the right, or quiet and effusive, like the one shown here on the left. A simple way to classify the types of eruptions is in this simple 2 by 2 chart. We have either high viscosity magmas or low viscosity magmas, and we have either high volatile content or low volatile content. And those two viscosities and two volatile contents give us 4 types of eruptions. The most dangerous combination is a high viscosity and a high volatile content, which gives rise to explosive volcanoes like this volcano here, Sakurajima in Japan. Remember, what happens is that as the magma ascends, bubbles form, and as these bubbles form, they try to escape and try to expand, but they can't. So instead, they basically become locked into the magma and eventually blast their way out of the magma when it gets near the surface, producing an explosive eruption. Explosive eruptions also produce pyroclastic flows. Remember, whether or not the explosion produces a pyroclastic fall or a pyroclastic surge or a pyroclastic flow depends on the ratio of the pyroclasts to the hot gases. When there's a higher ratio of pyroclasts to gases, you can get from an explosive eruption such things as a pyroclastic flow, shown here in this nighttime image of Sinabung volcano in Indonesia. At the opposite end of the spectrum is the combination of a magma with low viscosity and few volatiles. Because there are relatively few volatiles, there are relatively few bubbles, and those bubbles that form can relatively easily move through the magma and escape. So they don't propel the magma out of the throat of the volcano explosively, and instead the magma just oozes out slowly, like shown in these pictures here of lava in Hawaii. These kind of lava eruptions are called effusive eruptions, and there are two types of lavas that typically occur. They're both named after Hawaiian words. The first is called pahoehoe lava. Pahoehoe lava is the most fluid type of lava. It produces kind of a ropey surface as the lava slowly oozes over the land and sort of collapses in these beautiful ropes, as shown in this movie here. The other type of lava flow is called an aa flow. Aa flows are formed from more viscous or sticky lava, producing sort of a pile of seeming rubble that slowly rolls over itself as the lava flow advances. Even though you can't see it, everywhere underneath the surface here there's red hot glowing lava. It's just that it's moving slowly enough to where the top surface can cool and form rock, this black rock, so it's harder to see the bright red lava, the actual moving flowing part of an aa flow. Spattering type eruptions are caused by the combination of a relatively low viscosity magma with a relatively high volatile content. What happens here is that there are lots of bubbles, but the magma is relatively low viscosity, allowing those bubbles to escape easily and expand easily. And instead of blasting their way out into a giant explosion, instead they forcibly push the magma, now becoming lava, into the air as sort of pea or larger size blebs of magma, which may rise a couple hundred meters into the air and then fall back to Earth. These kind of eruptions are characteristic of volcanoes like Stromboli, where they erupt a relatively low viscosity magma, but for reasons such as interaction with groundwater, there's a relatively high volatile content in that lava. The last type of eruption is produced by the combination of a high viscosity and a magma that has relatively few volatiles. This produces what I call an oozing type of eruption. By oozing, I'm suggesting, I hope, that the eruption, the actual flow, is very, very slow. In fact, these type of eruptions are so slow that you can't even detect that they're moving if you just look at them. You need some kind of time-lapse imagery like I've shown here in the bottom of this slide to actually see that this is in fact a very, very slow flowing lava flow. These lava flows typically are formed by rhyolitic or andesitic, that is silicic, or intermediate lavas that have very, very high viscosity and often occur after a main stage of eruption, in which most of the bubbles, most of the gas bubbles have already been expelled. So what's left behind is a magma that's got a high viscosity but relatively low bubble content, low volatile content. And without the bubbles, this kind of eruption doesn't become explosive, but instead it simply oozes out of the ground very, very slowly. Oozing eruptions can also sometimes produce pyroclastic flows when they collapse. This image here from Mount Unzen in Japan shows exactly that happening. We have an oozing type of eruption that simply collapsed, exposing suddenly all of this hot interior to the cold atmosphere and the low pressure of the atmosphere, and this permitted whatever bubbles were there to expand rapidly, fracturing the magma, fracturing the lava, and producing a pyroclastic flow. The style of eruption also determines the type of volcanic landform that is formed on the surface. For example, here I've shown pictures of all different kinds of landforms. These are all volcanoes, even though they look really different. Effusive eruptions of low viscosity lava produce what are called shield volcanoes. A shield volcano is a very, very broad volcano with relatively low slopes. It's called a shield volcano because it looks like an old Hawaiian warrior's shield laid face down on the ground. The low slope of these volcanoes results from the fact that lava erupted from near the summit can flow so far away from the vent because the lava is relatively runny. And so it's able to travel far away and doesn't accumulate or pile up near the vent, producing a volcano with very, very gentle slopes. Spattering eruptions like that of Mount Stromboli that I showed a video of earlier produce what are called cinder cones. A cinder cone is simply an accumulation of usually lapilli or coarser sized pyroclasts that accumulate into a loose pile of material near the vent. Cinder cones are relatively small volcanic features. To demonstrate this, here I've shown an image, a Google Earth image of the shield volcano of Mauna Kea on Hawaii. And the surface of this shield volcano is peppered with zillions of little cinder cones. And you can just see how much smaller they are than the large mass of the shield volcano, which is over 20 miles across. Explosive volcanoes can produce several different types of landforms, one of which is called a composite volcano, sometimes also called a stratovolcano. Composite or stratovolcanoes are the classic conical volcano shapes like this image here of Volcan Arenal in Costa Rica. Stratovolcanoes are characterized typically by interlayers of pyroclastic material, tephra, and lava. So these are formed from volcanoes that can erupt either tephra explosively or relatively viscous lava flows at different times. So you end up with a volcano that's not made up of just one type of material, but two different materials that are interlayered. And that gives rise to this sort of classic, beautiful, conical, steep-sided mountain. Stratovolcanoes are really some of the most iconic volcanoes that you may have heard of. Things like Mount Shasta, Mount Rainier, the beautifully classic Mount Fuji in Japan, and the one I showed you earlier, which was Arenal in Costa Rica. Although composite volcanoes may seem really large, like Mount Rainier, they are in fact much smaller than the largest shield volcanoes. This comparison shows the relative sizes of Mount Rainier, a seemingly really large volcano, a composite volcano that looms over the city of Seattle, and Mauna Loa, a large, very large shield volcano found on the Big Island of Hawaii. And you can see that Mauna Loa is many times actually larger both in height and in width than Mount Rainier. Explosive volcanoes can also produce what are called giant calderas. These are huge negative features on the Earth's surface produced not by the construction of a positive feature, by the accumulation of lava or tephra, but by the hole left behind when a giant portion of the Earth, the volcano itself, has been literally blasted away. So what they are is basically giant holes on the surface of the Earth that represent the former place of a giant volcano. The eruptions that give rise to giant calderas are the largest, most explosive eruptions on Earth. They have been called by some volcanologists supervolcanoes, and Yellowstone is an example of a supervolcano. When these volcanoes erupt, which they do very, very infrequently, they produce the largest types of volcanic eruptions ever recorded. This image here is of a Pollo caldera in Nicaragua. You can see that it's just basically all that's left is a giant hole in the ground that's now occupied by a lake. Another rather well-known example in the United States is Crater Lake, which is actually a caldera. Okay, once again, this huge lake is filling in the hole that was left after the eruption of Mount Mazama occurred. Here's yet another example. You can actually see these caldera features from space. Here is an example of one of the largest on Earth, called Toba caldera in Indonesia. This is once again filled with a lake, and the distance across this is about 50 miles. So this is not a small feature. You can imagine how large this volcano must have been and how large the eruption must have been to basically evacuate this huge area and leave behind this pit, essentially, that's 50 miles across. The stages in the construction of a giant caldera look like this. So you have some kind of absolutely giant magma chamber underground that takes a very long time to fill with an enormous amount of magma. When that volcano finally gets ready to go, it goes in the most spectacular fashion possible, basically evacuating all of this magma in a relatively short period, in a matter of days, perhaps weeks, perhaps as long as a month. During that eruption then, this magma chamber is essentially emptied. Almost all of the magma gets erupted either as pyroclastic falls or as pyroclastic flows or whatever. It gets jetted out the top of the volcano, leaving behind a giant hole in the ground. The upper portion of the volcano then simply collapses down into that vacated caldera. Vacated magma chamber, and that's what causes the depression along the surface. So it's a collapse feature. The giant caldera is a collapse feature formed when the surface rocks collapse into the emptied magma chamber. That depression then is very often filled with groundwater to form a lake, like we saw at Crater Lake or a Pollo caldera. Finally, the last type of volcanic landform to know are what are called lava domes, and these are produced by oozing lava flows, and they look just like what it says. It looks like a dome of lava. Remember, this is a very, very slow moving oozing type of highly viscous magma, and they form a plug or a dome that's very often found within an existing caldera, like this example here. Here's yet another example of a caldera, a collapse feature that's been filled with a later oozing type of eruption, producing this humped dome in the middle of the caldera.